Alrighty, so this video we will be discussing the next method of heat transfer. Last time we did conduction. We're going to skip convection and go straight to radiation. Radiation heat transfer, or the heat transfer by radiation, as I discussed in the first video about these three methods, basically has to do with as an object gains heat energy, the molecules of that object gain this energy, and what generally happens is the electrons bound to those atoms and those molecules start to vibrate. And generally speaking, those electrons, I should say, if I were to make a little diagram of it, let this be the nucleus, of course, and we'll have a little set of electrons. And we assume, just for the sake of simplicity, the old orbital style of model for an atom with its electrons. Of course, we know through quantum mechanics that it's more complicated than this, but this model will help us to understand what happens. Well, what generally happens is you will have certain energy levels that these electrons can exist in. That's kind of the quantized state, which makes up quantum mechanics. But you can have electrons in certain energy levels, certain orbitals, if you've seen chemistry. And as an atom, as a molecule, gains energy, gains heat energy, one thing that can happen is this heat energy can come in, hit an electron, or be absorbed by an electron, and that excess energy can shoot this electron up to a higher energy level. If this original energy coming in, I'll call it a photon, it's a particle of light, it's a unit of energy coming in, hits this electron, and it's of a certain size, it's enough to bring this electron to a higher energy level, then this electron will now exist at this higher energy level. It's called an excited state. Which is fine. This is totally fine. It doesn't change the molecule. It doesn't change the atom. It's still the same atom. It's still hydrogen or helium or whatever it was before. It's just that one or some number of electrons were excited to a higher energy level, but they still exist there. The problem is, it's difficult for this atom to have its electrons exist at a higher energy state than is necessary. Just as, obviously with people, you may at some point drink a cup of coffee or have a Red Bull or something like this, and you have a lot of energy, and you go do work, or you're playing games on a computer, or whatever it is. Eventually you tire out, and you just crash down and you get tired, or whatever the case may be. Well, the same thing happens with these excited electrons. They cannot exist at this higher energy state for very long. So eventually, that electron will crash back down to its lower energy state, but in doing so will give off some energy. The amount of energy it gives off is equal to the energy level, or the energy gap is the formal word, the energy difference between the original state and the new state it gets to. Just as this incoming energy coming in originally had to be big enough to kick the electron up to the higher state, when the electron falls back down, it must give away that energy it took in. And so this happens all the time. In fact, a very unique version of this type of thing is what allows for lasers. Light amplification through stimulated emission of radiation. This is lasers. What I'm talking about is a slightly simplified, more general version, but you can see an electron absorbs excess energy, gets excited, loses that energy eventually, and gives off that energy back. Well, obviously, this energy is kind of a transformation of energy, this difference here. The energy that originally comes in could have come in as light, but it also could have come in as heat or friction. Let's say you have a whole bunch of these molecules, in a solid, and they're all jiggling around against each other because they're really hot, and that's what hot molecules do. They vibrate really quickly as they start hitting each other. And just through those collisions, you could accidentally knock one of the electrons to a higher state. And then that electron will knock back down again, and in doing so, send off light of a certain energy, whatever that energy is. And this is what radiative heat transfer is. You apply heat energy to an object, and you keep applying this heat energy. Eventually, enough energy goes into the molecules of this object to excite the electrons to very high energy levels. Eventually, it can't sustain that, so those electrons crash back down to their ground state energy, or at least the lowest energy state they can get to. And in doing so, will give off light. And that's why, if you've ever seen, charcoal in a barbecue pit, when you light it up, it gets red hot. Or if you have an electric stove, the little heating coils get red as they heat up. All sorts of things like this. We've seen, obviously, why the sun is yellow. And that is because the light that is sent off when those electrons crash back down to a lower energy level is of a certain frequency, a certain energy, that is in the visible region of the spectrum. In fact, whenever you see heat vision glasses or night vision glasses or things like this, what you're seeing is the fact that even objects that you don't think are giving off light, if you look at yourself or you look at the book or you look at the piece of paper you may be writing on, it doesn't look like those objects are giving off light because they're very hot. But actually, if you have infrared glasses on, what you'll find is these objects are hot enough for the electrons to be sending out light, sending out energy, whose frequency range, whose energy level, is in the infrared spectrum, what's invisible to our eyes, but not invisible to specialized glasses or goggles. And that's why night vision works, or that's why heat vision stuff works, because all objects, no matter their temperature, are giving off light. It's just that it's not enough of a high energy for our eyes to be able to visibly see it. And of course, you can also feel it. You put your hand next to a turned on light bulb or things like this, you can feel the heat coming off of this object, as well as see the light emitted from the object. So this is the conceptual view of what radiation is and how it works. What we're going to be more interested in, of course, as usual, is what types of calculations can we make? And so that's what this is going to start. The main equation, just like with conduction, there's one equation we're going to use to calculate the amount of heat transferred by radiation, and it goes like this. The heat transfer rate, Q over T. So again, this is called heat transfer rate. It's the amount of energy per second. You could also call it the power, because that's what energy per second is. The heat transfer rate due to radiation is equal to a number called sigma. Now this number is a constant, and it is called the Stefan Boltzmann constant. And it's just a number that has to be plugged into this equation because of the units we've chosen. Obviously, in the universe, the actual fundamental universe, a meter is meaningless. It's an arbitrary length. A second is an arbitrary time, and things like this. And so because of this, when we make equations using units that we're used to, a lot of times the numbers don't come out right unless you modify them with some kind of a constant. The same is true if you remember for things like gravity. If you remember, the force due to gravity is G m1 m2 over r squared, where G is a constant, the universal gravitation constant, or what you will find when you learn about electricity and magnetism, the Coulomb force, the attraction or repulsion between charges, is some K, Q1, Q2 over r squared. Again, there's a constant there purely because of the fact that units are weird and the answer doesn't come out right unless we modify the number using a specific constant. And so here the constant just happens to be this number, which of course you'll be given on a test or whatever. You can Google it. It's easy. You just Google Stefan Boltzmann constant and you'll see what the number is. So it's this number, sigma, times another number called epsilon. Now this has to do with how easily does your material radiate energy. And this is called the emissivity. So if you happen to have a metallic object, it emits energy much more easily than if you have a styrofoam object. And so emissivity is kind of like the constant that tells you what material we're talking about. And so if it emits 100% of the energy that it could, you would call that emissivity 1. Or if it emits at 75%, then it would be 0.75. And so given a question, you would be told, you have a solid sphere that emits at 33%, blah, 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 blah. Then you'd know emissivity, this epsilon number, is 0.33. It's a decimal where 1 is 100%, 0 is 0%. Okay, then it also depends on how big is your object. Obviously, the bigger the object, the more places light can be sent out from. And so, if you have a very big sphere, there's a lot more places this energy can be sent away from the sphere than if you have a very tiny sphere. And so, obviously, the heat transfer rate should depend on what's called the cross-sectional, I'm sorry, not the cross-sectional area, the surface area. And so, just so you know, to have it, the surface area for a sphere, if you don't know the equation, is 4 pi r squared. And the surface area for a box, well, let's see, there's length times width is the area of one side, and then how many sides does a box have? 1, 2, 3, 4, 5, 6. So it'd be 6 times the length times the width. Okay. So depending on the shape of the object, you'd either use the surface area for a sphere or the surface area for a box. And then finally, the heat transfer rate depends on how hot is the object. The hotter the object, the more heat will be sent out per second. And the way it depends is the temperature of the object to the fourth power. Now, this is very unique. It's rare to find an equation that has a fourth power in it, and in fact, this one does. So a temperature to the fourth power, if you see that in an equation, you know you're talking about radiation. Now note, unlike every other equation we have had that dealt with temperature, this does not have the temperature difference. This is the pure temperature of the shape of the object. So if you're talking about a piece of metal, a spherical piece of metal that's at 1,000 degrees, well, you have to convert to Kelvin, because we're not talking about differences in temperature or the change in temperature. We're talking about the absolute temperature of the object. And so you must use Kelvin here. Do not use Celsius. If you use Celsius, you'll get it wrong. Now, I do want to note that there's a second way we can ask this question, which is very similar. I didn't go the same way, sigma, epsilon, A. But now, let's say instead of just saying, for instance, we have a star out in space, and the star is at 10,000 Kelvin. And I want to know how much heat is transferred after 2 days, or something like this. If instead of that, I said, you have a metallic spherical object that's at 5,000 Kelvin, and I place it in a refrigerator whose background temperature is 0 degrees Celsius, or let's say 273 Kelvin. This question does deal with difference in temperature, because obviously if the environment is really close to the actual temperature of the object, then the object itself is not going to radiate as much or as easily. So what you need to understand is, how do we show this particular difference in temperature? Because there's two ways to do it. We could do T of the object minus T of the environment to the fourth power. Or we can do T of the object to the fourth power minus T of the environment to the fourth power. These two things are not the same. Obviously, this one has cross terms. If you actually try to do that multiplication, if you actually take the fourth power of this binomial, you're going to get a whole bunch of cross terms. Whereas this doesn't have cross terms. It's just the main terms to the fourth power. So these aren't the same. Which is the right one? It turns out the right one is the second one. The equation, when you're given the object at a temperature and its environment at a different temperature, is the temperature of the object to the fourth power minus the temperature of the environment to the fourth power. Okay? And likewise, if I want to know how much heat is transferred in a certain period of time, I would just take the T and move it over here. And plug in however much time we're talking about in seconds. But these are your two big equations. It's actually one equation, but written two different ways, depending on the question itself. And so let's take a simple example. Let's say we have you have a solid metal sphere of radius 50 centimeters at 1,000 degrees Celsius. Calculate the heat transfer rate by radiation if it's a perfect radiator. First thing to note, what the heck does perfect radiator mean? this means emissivity is 100%. It emits perfectly, so it emits at 100%. That's what emissivity means. Now, what do we do? Well, here we have a question about radiation. What's the equation? Heat transfer rate is equal to sigma epsilon A T to the fourth. What do I need? First of all, I need to know sigma. Sigma, Stefan Boltzmann's constant, is 5.67 times 10 to the minus 8. And if you want the units, it's joules per second meter Kelvin to the fourth. Okay, so that's the constant. That's something, of course, you can have on paper. Given a test, you'll have this on the test, so you won't have to memorize it. But if you ever forget it, just Google Stefan Boltzmann, and you'll see it. What else do we need? We need emissivity, epsilon. Well, we know it's a perfect radiator, so that's 1. We need A, the surface area. We're talking about a sphere, so that's 4 times pi times r squared, which is 4 times pi times r, the radius. I'm told the radius is 50 centimeters. Of course, centimeters is bad. I need meters. 50 centimeters is the same as 0.5 meters. So 4 pi times 0.5 squared. That gives me, guess what? 3.1416. Gives you pi. And then we need the temperature. We're told it's 1,000 degrees Celsius. Celsius is bad. We need to convert to Kelvin. And of course, to convert to Kelvin, we just take the Celsius and add 273 to it. So 1,273 Kelvin. And there we go. Sigma, epsilon, A, and T. So Q over T equals 5.67 times 10 to the minus 8 times 1 times 3.14 times 1273 to the fourth power. And what do we get? We get 467,785.27. Of course, if you want this in scientific notation, that's 4.68 times 10 to the fifth joules per second. Either one of these answers is perfectly fine. And that's all there is to it. Given a question on radiation, these are the things you need. Right here. Sigma is always the same number. It's a constant. Epsilon, given in the problem, either perfect radiator or radiates at 75% or emits at 100%, however it'll be said. You have emissivity. Surface area depends on the size of the object and the shape. If you have a sphere, 4 pi r squared. If you have a rectangle or a box, I should say, it's 6 times length times width. And the temperature, of course, must be in Kelvin. The only difference here in any other question I could give would be if I told you the background temperature as well. Then instead of T to the fourth, it'd be T of the object to the fourth minus T of the environment to the fourth. And the only other thing I can do other than that is I can give you how much time we talk about and ask how much energy will happen in that time. And so, like I said, you just multiply the T to the other side. You'd be solving for Q. Q equals sigma epsilon A T to the fourth times time. And then you'd have some answer in joules. So, I hope this is helpful. I hope it's understandable. Of course, I will post a video in the future with some example problems on this topic. But as you can see, this topic isn't all that complex. There's not so many different ways I can do this type of problem, which is a good thing. But definitely practice them. Practice the problems that are on Canvas as well. You should be fairly close, if not there, being able to solve any of the problems that are on that practice problem set. If you're having trouble with any of them, of course, as always, please email me. I'll be happy to answer whatever I can. But keep an eye out on Canvas. Make sure you're keeping up with whatever homework problems are posted, any practice problems that are there, and you see when new videos are posted. That way, if you don't get an email from me about it, at least you know it was posted when it is. So, good luck. Until next time.